Yeah, this is going to be a quick video on Monte Carlo simulation using a semantic PLC and a Monte Carlo simulation program in TI Portal. This is going to be the classical Monte Carlo simulation, finding the number pi. So you can see in the square, this is taken from Wikipedia, they have a nice figure there. So the idea here is to have random numbers, calculate the radius here, and if that's less than 1, the radius here, then of course it's in the quadrant, and each time you run this, you increment a number for the square here, and then you use the property that the area of the quadrant here divided by the area of the square where the quadrant is is pi to the 4, and then we just multiply by pi, and then we have an approximation for pi. And here is a pseudocode for this way of doing it. Now let's see. So here is the PLC code. It's a quick and dirty code, but it's according to one user before. 2 random numbers we generate. We calculate the radii, the r, and then of course for each iteration here we increment in the square by 1. All are in the square, and if they are less than 1 or less or equal to 1, then we integrate in the quadrant. And now, of course, the number in the quadrant divided by the number in the square times 4 should now be the approximation for pi. Of course, we have to test this. Yeah, we are using this random number function here, generate number function, and yeah, this was the problem, of course, where here are the data areas that we are going to test it. So I've just put in some numbers, some prime number for seed for A and B random number generator. Here are the random numbers, and here are the increment, the long inch in the quadrant and in the square, and here's the pi approximation. So that just corresponds to not that, but this one. These are the variables here. Okay, we'll try to run and see if we are getting close to 3.14 and something. And here is just execute. So if you look at here, it just says if not execute is not true, then we just return. So we are not running the program. So if I double click on execute, it's going to start to run. And again, this is a PLC, so it just generates 2 randomness per program run or iteration, and then you just accumulate these and then just calculate here. So 3.14 and something. And this also checks the quality of your random number generator in a way. And of course this can run as we are running on long integers, 64-bit numbers here. This can run forever. But of course the algorithm that's being used here, this one, would repeat itself eventually. So 3.14, 3.14, 15, 65, something, yeah. Of course I could have just taken an inverse cosine to -1 or something to find pi here too. To see what it is, but it's 3.14 something. And also, if those numbers, that's exactly 1, now falls in the circle. But again, as we are running on long real numbers, 64-bit numbers, could make a difference. Not much. Well, this can run. Of course, we can also just in the code just turn it off and see. And here you could just, if you want to run this off, you can load it with start values, Okay, if you want to change that one and say, okay, we say they have to be inside, compile it, download, load it. Nothing back to the instance data, no, the data block, because this can be removed. This is for accessibility from HMI. I don't think this is something that we want to show, but now we have changed a little. Where was it? It's this one. Run again. This is pretty fast. This PLC is running more programs. It's running an Model Predictive Control algorithm too. But to the random number generator, what could you use it for? As we talk about Model Predictive Control, one way of finding optimum trajectory in Model Predictive Control is to use genetic algorithm. They use random numbers, for instance, to pick candidates out of a batch of individuals and see how they are performing here. So that's is one way, or you could use this. The modern PLC, we're running pretty high performance microprocessor, microcontrollers. They are capable PLCs. Well, this is due to the random number generator. So, but eventually it would run. It would be 3.14. Of course, we removed. Yeah. Okay, it should be a little less because, but again, the chance of hitting 1.0 exactly here is not that great in the code. So that was a quick introduction using a PLC to run the standard Monte Carlo simulation example where you find pi just using random numbers. It's kind of a nice one. But again, like I said, you could use it for something, picking out of a batch of individuals for genetic algorithm or something like that for Monte Carlo simulation.